Okay, okay, very good. We can experiment with that. So the most important thing first is that this is work with my students. She will be in the market this year for postdocs. Shanshan just graduated and she joined Google. Ashish joined Google a few years back. Dave is doing MRI with deep learning related to this work. Eric joined Google Research. Jay is a new student, and Ajay are still current students at UT Austin, and Eric Price you probably know. So there is a subtitle: "The future will be unsupervised." So I'm just very much arguing here for unsupervised techniques. And okay, so that's the first thing. Supervised learning in practice works pretty well. You know, if you have a gazillion labeled examples, if things are not going badly, and the typical way that things can go badly in supervised learning is when there's some sort of distribution shifts. So distribution shifts can happen because somebody's manipulating with your input for your classifier, or because you bought a new camera, or because you changed the lens, or because you went to a new city, or because something that you don't even know is going on in the way that your training data changed from your test data. And that's actually super hard to even test or know what's going on, right? So I say that even if you want supervised learning to actually work well without the star, which means in a more robust way, which I think is one of the key challenges, you have to understand unsupervised learning. So you need ways to model high-dimensional distributions. So basically, my favorite and the current way of describing high-dimensional distributions is what I call deep generative models. And I may use the term DGM for that. I will explain what that means. And so the actual more precise talk is some results and some open problems for deep generative models. That's what I will talk about. So there's this paper we had in ICML 2017, Compressed Sensing with Generative Models by Bora et al. So I will be talking a little bit about that. I don't know how many people have seen this work. How many people know what's going on in this paper? No. OK, so no. So most people do not, as I was anticipating. So I will be spending some time on this. And it's very naturally ties in with some of the things we have been talking about in this workshop. And then there is some ongoing work that I will spend the second half of my talk talking about that uses a different type of generative model. That's called invertible generative models, and how to use them to do conditional sampling. So how to model high-dimensional distributions. So, you know, one idea is, OK, you just say they're Gaussian, and you have to learn a covariance matrix, and that's fine. That works. There's a ton of work on that. Now, there's been two other ideas. And naively, when you have n variables and random variables, a joint distribution, even if they're binary, has 2 to the n parameters, right? So you cannot even think about writing down such a table. So you need some technology to get in high dimensions. And there's really fundamentally, I would like to say, probably really two huge lines of work that have been historically used. One of them is factorization or conditional independence that has led to this beautiful and rich theory of graphical models and Bayes nets, and you know, Markov chains, of course, in the simple case. And I want to say this is, of course, extremely beautiful. Mathematically, it's actually extremely useful and extremely successful. Did you bring a graphical model with you today? Do you carry one on you, or a couple? So I'm a coding theorist, yes. So how many are there? So LDPC codes, low density parity check codes, which are graphical models, which are used to do error correction, are shipping in a million places that you're carrying on right now on you, namely in every 3G chipset, every Wi-Fi chipset, every hard drive, and every SSD have LDPC codes that are performing inference over graphical models. That's an extremely successful technology and theory. The second type of extremely successful and extremely rich theoretically way to handle high-dimensional distributions and high-dimensional data is sparsity, as you know. And it's typically not sparsity in the standard basis, even though as a theoretician you may work there. But you say, OK, it's sparsity in a known basis, or even in a basis that I can learn in a data-driven way, which is like dictionary learning, all this stuff. Did you bring your sparsity-based technology with you today? Where is that? In your brain? No, we don't know that. No, so where is that used? Just a fun question. Where is that? How is that changing the world?
Camera.
What's that?
Camera.
Okay, so where in the camera? So in the sensor of the camera? Yeah, maybe. I mean, definitely it's used in all the compression standards, okay? So every time you use JPEG or MP3 or MPEG to compress an image or a video or an audio, these standards are using sparsity in DCT or wavelet basis to compress data, right? So it's fancier, of course, but it's basically really that with a few extra bells and whistles and entropy coding at the end, the lossless part. So compression really, by the way, for information theorists, this is extremely pleasant because information theory started by Shannon in 1948 has really two pillars, right? Channel coding and source coding. And channel coding is really this technology, and source coding is really this technology. So it actually is very pleasant, for me as a coding theorist to be making this analogy. And also, by the way, compressed sensing techniques, which are based, of course, on sparsity, are now shipping in all MRI machines as algorithms that people use every day, and in other medical imaging modalities. So that's all great, but this is not what this talk is about. This talk is about something else. It's about the fourth way to capture high-dimensional distributions, which is what I call deep generative models. And the idea there is you take some simple randomness, like an independent Gaussian or a uniform, and you transform it with a complicated function that you learn, okay? And the function is just going to be basically matrix multiplications and ReLUs. So nonlinearities of the simplest kind. And depending on how you actually learn this function, there is a bunch of different families of deep generative models that people call, so there's the vanilla one is autoencoders, and then there's vanilla variational autoencoders. Then there's GANs, which are trained in an adversarial way. Then there is untrained deep generative models, which is a shocking phenomenon that appeared 2 years ago, that you don't even need to actually train these weights. The mere fact that it's a convolutional topology will produce data that looks like natural images. So this is a fascinating and extremely poorly understood phenomenon that I can talk a little bit about maybe at the end. Probably we'll run out of time. And then this is the fancier, not the fancier, probably the most appealing to a theoretician. So the fancier theoretically flavor of deep generative models that are called invertible flows. And by the way, the nomenclature here should be making it clear that the people who are coming up with these names are not theorists, because of course flows mean something that has nothing to do with these. And okay, invertible is a sensible word. So we'll be talking a little bit about invertible flows in the second part of the talk, and then you don't really need to worry how they're trained other than the last one. So to me, it's just really a machine, a neural network that takes a bunch of random independent variables, multiplies by a matrix, ReLU, matrix ReLU, etc. And then from random noise here, you get something that looks like a human face or a human bedroom or like a human, or a dog or natural images. And I must tell you, honestly, I think it was 2017, and when I saw this, I was working on causality, I think in sparse PCA, and then I saw this paper, DC GAN, that did this. I'm like, shit, I can't believe this. I can't believe that these things are actually coming out from matrix multiplications and ReLUs. It's amazing, right? So now we've been seeing much better models, so these are actually not even state of the art, but it is remarkable that we are able to do this right now. So, and by the way, these models have long-range correlations, of course, because if one eye is blue, the other eye is very likely to be blue. These models learn structures that are incredibly interesting and complicated that graphical models or any other technology that we love and use every day are really not able to do. All right, so this is actually training a generative model from data. This is a DC GAN architecture. So again, reminding you that this is not a real person. This is just some random noise that was multiplied by some matrices, and we can generate things that are now passing what we call a visual Turing test, which is you cannot tell if they're real or fake. And the same thing is happening in audio. The same thing is happening in text. And it's extremely interesting area that has very little theory. So what I want you to think about is that a deep generative model is simply a function that takes a low-dimensional vector. We'll see that for invertible, it won't be low-dimensional. It will be actually n. And maps it into Rn again. And it's simple. For all the cases I care about, it's differentiable almost everywhere. In fact, it is just a composition of matrix multiplications and ReLUs. And somehow you learn the matrices, which is what GANs and VAEs are different about. And this is learned from samples. All right. And the other thing that you can do, of course, is you can pick your favorite z. So z here is 100-dimensional vectors. You can pick your favorite z, which is 1, 0, 0, 0, and your second favorite z, which is 1, 2, 3, 4, 5, up to 100. And then you pass z's through this function g of z, and you're going to get human faces. So what you want to test here is perhaps this network simply memorized 5 or 10 faces, and it's just showing me one of those 5. So I want to see if I smoothly travel on the manifold of human faces, or if I have to simply memorize, 5 of them. So the test here is to see if in the middle of this linear interpolation, after it goes through this function, we remain on what look like different human faces. So this is the experiment that we have done and other people have done also, and you see that it stays natural. So we don't know if it has learned all human faces, but it has definitely learned a very interesting manifold here. All right, very good. And this is a better one. It's called BGANs, that basically they produce amazing images. You cannot tell if these are real or generated. So that was kind of where I got like really excited, but I'm like, okay, this is cool, but what can you do with it, right? So that's the question. So they're pretty, but is there something useful we can do? And other than some really niche applications of let's generate, fake LinkedIn profiles or something like that, which are not really useful. So the point I want to make, of course, if you haven't seen the Bora paper, is you can do a gazillion extremely useful things with this. Specifically, you can solve what we call inverse problems. And inverse problems include denoising, inpainting, which means missing data, completing missing data, compressed sensing, which means a linear inverse problem with a random IID Gaussian matrix, outlier detection, source separation, which means, for example, you see an image or an audio that is, let's say, somebody speaking on top of music. You want to separate somebody speaking from the music if you had a generative model for the thing you want to separate. Magnetic resonance imaging, which is a specific type of inverse problem, or phase retrieval, which is another special type of inverse problem. And there's a gazillion more. Basically, once you get into this frame of thinking, it's extremely useful to have a deep generative model because you could really learn so many things about your data. And everything here is, of course, unsupervised, the way I'm setting it up. So I'll tell you briefly about this paper, and then we'll get into the new stuff. So the general setting is I have a known measurement matrix, or it's called the forward operator in inverse problem nomenclature. It's called the design matrix in linear regression. You have an unknown vector and an unknown signal, which is the thing you want to retrieve. And you observe some projections of the unknown thing. And of course, you're in the setting where the dimensionality of the unknown vector n is bigger than number of measurements m. So as you know, of course, in this case, there are infinitely many solutions to a system of linear equations. So there's no hope of retrieving the unknown vector. So you must make an assumption, a structural assumption. So actually, when you invited me to this workshop, I'm like, oh, that's great. That's exactly what I'm doing. Because we're trying to find some structure here to make this problem have any hope of being retrievable, right? And the standard assumption that we make in compressed sensing is that this vector is k-sparse. And then, of course, you say, OK, I would like to find the sparsest vector in this that satisfies my linear measurements. This is the noiseless case. This is NP-hard, of course, so you relax it to this problem, which is called basis pursuit. If you also have noise, you do lasso. And there has been a million papers about under what conditions can you prove that the solution of this tractable linear program will give you something that's close or is the same to this NP-hard problem, right? So many of us have spent half of our career analyzing these types of problems. I mean, the very well-known papers by Donoho, Candes, Tao, etc., define these conditions like restricted isometry property, restricted eigenvalue condition, and so on, that are properties that have a random matrix will satisfy if you have enough measurements, typically k log n over k. K is the sparsity, and logarithmic in n, which is great, the ambient dimension. And if you have such a condition, then the relaxations will be tight or near tight. And this is a very rich theory that in this crowd you're all probably familiar. Are we all on top of this stuff? So very good. So, and of course, in inverse problems, there is some unknown vector. X corresponds to, let's say, the pixels of the brain that you want to observe, and you don't want to directly cut the brain open to look at them, so you shine some X-ray or something through this physical modality, and you observe a linear projection over these unknown pixels. That's the case where you're this type of high-dimensional regression appears in imaging, right? And real images, as I said before, are never sparse, except if they have only a few pixels on, but they can be sparse in a known basis or in a basis that you learn from data. So this is like a linear generative model, but now we're going to make deep generative models instead. So sparsity is a decent model, as we said, but now we have much better data-driven models, which we call deep generative models. So the key idea of this talk, in general, is if you have a paper somewhere in the past that was doing something with vector x being sparse, I say replace that with x is in the range of a deep generative model, and now you have a new extremely interesting problem. So, and in some cases you can actually generalize the theory. By the way, a new fact that came out, I guess, a few months ago by Eric Price is that the set of vectors that are k-sparse is a strict subset of the vectors that are generated by a deep generative model. And basically he constructed, not a deep one actually, two-layer neural net that has in its range all k-sparse vectors. So I don't know if you, and it's polynomial size. So this, I did not know that you could do this, but it turns out that this is a strict generalization of sparsity. Is that making sense? Very good. So, okay, so the question is, okay, assuming that x is in the range of some deep generative model, how do we solve inverse problems? So the idea is, again, you have an unknown vector, you observe a few linear projections of it, but now it's not sparse. Rather, you assume there's another neural network here, or a function, that produced the vector you're trying to reconstruct. First question here is, what happened to sparsity? Before we're saying sparsity was k. Where is k here? Question to see who's still with me.
Z star.
So the dimension of z star is going to be the corresponding concept to sparsity, right? So the dimensionality of the latent code, as we will call it, is going to correspond to the dimensionality of the manifold, which will correspond to sparsity in the vanilla case. Is this making sense? Okay. So we're replacing sparsity with a neural network. Before, to recover, we were using L1 relaxations. What's the recovery algorithm now? So it's the same way you do anything in neural nets, right? So let's solve one problem first, the easiest one. I give you an image, x1, and I simply want to do what's called inversion or projection. I want to find a z so that g of z is as close as possible to this given target image, okay? So how would you solve this problem in deep learning? The same way you solve any problem in deep learning. You write some loss, and you do gradient descent, right? So what's the loss? The loss is going to be here, all right, g of z, the generated image, minus the target image. Let's do L2 norm. You can do fancier if you want. But L2 norm of this is a differentiable function of z. So you start with some random z. You do gradient descent in z to match the measurements, okay? This is, of course, a non-convex problem. It's actually provably NP-hard. And we have actually shown several hardness results recently. But for some types of generative models, it is actually empirically efficient to just run gradient descent, and it works. So this is the actual reconstruction. So we said that in our paper, and many other people said the same thing, because it's a pretty obvious thing to do, right? Are we together? Because if we're not here, it's going to get very boring in a minute. All right? Great. So then the next problem is in painting, where you observe an image, but you're missing some data. So how would you invert now, given that you only have partial observations? So you are going to search for a z that agrees with this image only on the boundary, right? So you write the loss function that is, this is now the projected image, like the measurement, you can write a matrix, of course, that observes only the pixels you see, and you say, after I measure the dreamed image, it must agree with my observations, and then you do L2 norm. This is still differentiable, and you run gradient descent on this, and you get this image. And this is shocking, right? This quality of in painting is shocking. Like wavelets or anything like that would never be able to do anything like this, because they don't know people have noses, etc., right? They just know that natural images are sparse in a wavelet basis. So the quality of these reconstructions was super good. Another example is super resolution. Again, you observe a blurred version of an image, that's another matrix again. You can write a matrix that blurs an image, convolves it with a kernel, let's say Gaussian kernel. Again, you just search for a z so that the generated image, after it has been blurred, agrees with the blurred stuff I get to look at, right? So again, you get an excellent super resolution reconstruction. Yes, sir?
So for these examples, is the uncorrupted image generated from the same model, or it's?
No, the uncorrupted image is definitely not in the range of the GAN. The uncorrupted image is like my image or some image I get on Google. The ideal situation is, so the data set we use has a test set. So it has images that are not in the training set, but are correctly calibrated. All the color temperatures are the same. So that's the easiest case. But my favorite case is not even that. I take my own picture, and I try to project it. And that's, or Kostis, actually. So actually, my own picture was not working for this GAN because I have a beard. So like the moment you have glasses or you have a beard, for example, the specific GAN that we were using in this paper was very fragile to any change of distribution. Or also, if you tilt your head a little bit, if your camera doesn't have very good color calibration, it was fragile to distribution changes that you may not even know about. But you will certainly take images that are not in the training set, okay, or are not in the range. Very good. So this is the general algorithm we proposed. And the other thing that you can realize is that A doesn't have to be a matrix. It can be any differentiable forward operator. So we can solve a gazillion problems like this. And a gazillion papers have been written that basically propose this empirically. Yes?
So I'm curious if there's a parallel between this and, let's say, the more supervised ImageNet types of things.
Very good.
You see this progress of maybe we're going to increase the size of a deep net by a factor of 10 or 100 every few years.
Mm-hmm.
And then we get very small improvements.
Mm-hmm.
So for example, for in-painting, I mean, do you get better performance when you have these giant deep nets? Do you have like
very good
similar qualitative picture to sort of the supervised story?
Very good. I will hold that thought for one or two slides, and we'll talk about it. Thank you. So we'll get into that. It relates to the complexity of the number of. It relates to the number of measurements. Is the short answer. But yes. So this is the algorithm we proposed, right? And the key idea is because this is a differentiable operator and because this whole box is differentiable, we get gradients. Like I tell you, once you move z a little bit, how much this loss will change using backprop, right? So it's key that everything end-to-end is differentiable, and backprop is a key of actually running this algorithm, right? So a comparison to just lasso, which I use sparsity. This is the reconstructions you get with lasso in DCT and wavelet domain, and this is with our DC GAN, which wasn't even a very good GAN. It was a decent GAN, but now there's much better ones for. And depending on the data set, you need to train a generative model for a different data set. So, and this is the other, and that's where I will answer your question. These were sparsity-based methods here, and this is basically our method, DC GAN and DC GAN with regularization. The point is that you get almost a 10x improvement in measurements, which is extremely important for medical imaging. If you could do medical imaging with 10x fewer measurements, like patient discomfort and many things you could image that you would not be able to image before. So one interesting question here is, as you can observe, here I have number of projections, number of measurements, and reconstruction error, right? After a while, you see that the generative model does not get any better, whereas the sparsity-based method gets better. Why is that? And which will relate to your question. Do you have any intuition why it stops getting better here? So after this point, you have pretty much reached the best dream the generative model can produce for this target image, right? So you have basically saturated the representation capability of the generative model. Adding extra measurements no longer helps you. Now sparsity, on the other hand, is quite expressive if you increase, especially if you're allowing it to be less sparse, right? And here it's a soft, constraint on the sparsity. So sparsity can actually represent any image perfectly. It will give up on sparsity at some point. But the moment you're here, you need to throw away your generative model and buy a bigger one, right? You need to buy a generative model that has a bigger K because you have more measurements. So the answer to your question is, depending on how few measurements you have, you should be using a generative model because it's a trade-off, right? It's a trade-off between the expressiveness of the generative model and the economy you make in your reconstruction. Is that, yeah, very good. So this is the empirical results, and these empirical results were very promising. And I just want to emphasize here that it's not just us doing this. There has been a gazillion people, mostly from the signal processing community, that have been saying these things for a long time. So there's been model-based compressed sensing, projections on manifold with compressed sensing, and many other ideas that have been proposed. The difference of what we proposed versus all these ideas is we used deep generative models and backprop as opposed to other ways of modeling high-dimensional distributions. That was really the innovation. OK, yes, sir.
Is the size of your generative model, the number of parameters, bound by the input size, k?
No, the number of parameters are.
You can increase
OK.
the parameters, and just as you might.
Yes, sorry. I'm not messing with the weights of this network here. So the network is, somebody trained it. If you're recovering, let's say, images of dogs, somebody trains this thing and it knows dogs. I'm not going to mess with it. I'm only optimizing over this vector. That's very important. I'm only optimizing over the input of the generative model. I'm not changing the weights. Other people propose to also do joint training of input and weights. Right. And there have been alternating methods and so on. But in the theory I will present, this is assumed to be a known generative model. And it is assumed that the vector you're trying to reconstruct is close to the dreams of this fixed generative model. Is that making sense? OK, very good. So a theorem, I think, is next. Let's see. All right. So what can we prove? So you observe linear projections of some x star plus noise. You would like to solve this problem. This is the inversion or the projection, right? So you would like to find a z that minimizes, that explains, let's say, the measurements as well as possible. This is NP-hard, by the way, OK? But let's say you could solve it. If you could solve it, the theorem is this. If you make your measurement matrix random, with the number of measurements being k d log n, where k is the input dimension, d is the depth of the neural network, and n is the ambient dimension, then the reconstruction error you're going to get, so what is this? This is the best dream that the network can do, right? If this is not good, you should throw away the generative model, buy a bigger one. This is not my problem, right? But what I'm saying is that the reconstruction you will get by solving this problem is going to be close, a constant here, up to the best reconstruction you could hope to get with this generative model. And the important thing is there is no A here, right? The measurement matrix did not create a problem for you. So this is like a restricted eigenvalue condition not for sparsity, but rather for a deep generative model. Is this making sense? Very good. So the reconstruction accuracy is proportional to the model accuracy. And there's another variation of this result that says for any function that goes from Rk to Rn, if it's differentiable, where L is the Lipschitz constant of the function, you need k log L measurements to get a result like this. Okay, so slightly more general, as opposed to depth. So depth and Lipschitz constant are very related in the way we do this construction, because basically we just bound the Lipschitz constant by the maximum weight to the d, right? So this trivial bound that we have.
So for theorem 1, do you need a bound on the Lipschitz constant? Does that show up in?
Yeah, I mean there's different ways you can prove it, but basically we do an epsilon net in the input space, which is the k-dimensional space, and then we need to cover the distortion. So we need some way of controlling that. Yeah. So the technology of proving these things is very similar to the vanilla compressed sensing proofs, actually. And the network just comes in the mapping from Rk to Rn. So a technical comment, so there is restricted isometry property and all its variations that says all the sparse vectors are far from the null space of the measurement matrix, right? That's the simplest version. And basically it says your measurement process is blind to these sparse vectors. You better be sure that there are no sparse vectors that are close to the null space, because then you're screwed, right? So the general theorem we prove doesn't take sparsity. It says we define a set restricted eigenvalue condition. The set is the range of the GAN. And we say that the differences of pairs of generated images, right, this is going to be far from the null space. If this is true, intuitively, you expect that you will not be confused, because any two generated images are going to have a significant projection difference. So this is the key thing we have to prove. And the key lemma is that random matrices with k log L rows, L is the Lipschitz constant, will satisfy this set restricted eigenvalue condition with high probability. So this is like, if you're into this sort of proofs, this is the translation to RIP. Is this making sense? Okay. Very good. So this is basically the end of this Bora paper, and now I can talk about conditional sampling. And I have 15 minutes. 15 minutes? All right. Let's say I have. Unless there are any questions on this, we can take it at the end too. Okay. Conditional sampling. So invertible generative models is a fancier or newer version of deep generative models that have an extra theoretical property that for a GAN, for example, you can never get likelihood. Like you can get a Z, you can sample an image, but if I give you an image, you cannot tell me the likelihood of that image. And the reason is there can be multiple Z's that produce the same value of X. And we actually have proven in a recent paper that it's NP hard to check if a specific X is in the range of a generator. However, invertible models do not have these limitations. So when we say invertible generative models, you may hear names like Real NVP, GLOW, invertible ResNet, or neural spline flows. These are all different types of deep generative models that are invertible. And they're trained in a much easier way, just maximum likelihood, because they give you likelihood. So you don't have to solve this min-max optimization. You directly tune the weights to increase the likelihood of the data. These are actual samples from invertible models. You may think when you first saw this image that these look great, but if you look more carefully, they look a little freaky. Do you see it? So they kind of look great, but until you look closely, and then they don't look that great. But they're pretty good. Like this is not good, for example. So how do they work? So I want to show you the key gadget of invertible generative models, and I will prove something interesting about them. The key gadget in making all these things work is some way of so a neural network, when you're doing gradient descent, will not be an invertible function, right? And you have no easy way of enforcing it to be an invertible function. So this is one very nifty way of enforcing it to be invertible. So take a vector in Rn and split it in two parts, x1 and x2 prime. So this is n over 2 and n over 2. x1 passes as identity, so you get x1 here. But you also take x1, you pass it through some arbitrary network that produces n over 2 dimensional vector here, and you add it to x2. And this is what x2 prime, and this is x2. I want you to notice that this network is always invertible. Is this clear? So if I give you this vector, OK, you have x1, you just read it off. So you get x1. Then you take x1, you pass it through this network. You get this thing, you subtract it from this, and you get x2 prime. So no matter what network you put in there, this whole box is going to be invertible. Is that clear? OK, that's one of the key ideas for making invertible generative models. The second key idea is that the determinant of the Jacobian of this mapping is always going to have identities here. This is the derivatives of x1 with respect to itself. This is the derivatives of x2 prime plus n of x1 with respect to x2. So this is identity. And this is the Jacobian of the net. But I don't care about that, because if you take the determinant of the Jacobian, it's always going to be 1. Again, regardless of this neural net. So basically, this tells you, you can do gradient descent here. Don't worry about this. This thing will remain preserving and invertible. OK, so that's basically a key idea for invertible nets. So I can define a prior p of x using an invertible generative model. And the question is, given this prior, can I do what we call perhaps Bayesian compressive sensing, which means sample an image given the measurements. Before, I was just reconstructing. I was deterministically reconstructing. But now I would like to get some diversity. I would like to get some performance measuring the variability of the reconstruction. Right? So I give you half the face, and there's not one way to reconstruct. I would like to get a gazillion reconstructions and see how much I trust every pixel in the reconstruction. Okay? So here is there are many methods to do conditional sampling. However, they're very expensive or they're very fragile to changes in the forward operator. So I can talk about the limitations of other approaches later. But there's an interesting theorem that we showed that you may like. So even for an invertible model you can generate, and you can also give me any image, and I can find its likelihood. All right? But what I'm telling you is that it's provably hard to do conditional sampling for an invertible model. So what we showed is any invertible model that uses this gadget, the additive coupling layer, if you had a way to sample conditionally from an additive coupling layer, then RP is going to be equal to NP, which is like basically randomized polynomial can solve NP-hard problems. So nobody believes this. I'm not a complexity theorist, but I'm sure.
So this is over a worst case n?
So this is over any, yeah, so the technique is going to be, if you had a box that could conditionally sample for any n, then you can solve 3-SAT. And the technique is really pretty straightforward. If you give me a 3-SAT formula, my student found a way to design an n of x, a network, so that the network produces 0 if this given 3-SAT formula is not satisfiable, or it produces a very large value if x1, the input, is close to a satisfying assignment. Okay, so you can do this, you can build this such a neural network that does this. And then you condition on x2 being large. So the moment x2 is large, there must be x1 must be a satisfying assignment. So if you had a way to conditionally sample condition on x2, you would be able to sample satisfying assignments. That's basically the idea. Is that making sense? So yes, sir.
If RP is equal to NP, can you do it? Obviously, it's harder.
I don't know. I don't know. I mean, I don't think we have to worry too much, but yeah, I don't actually know if it's harder. No. But this is just a reduction we do. It could be harder, actually, yeah. So very good. And this is, by the way, n of x is a network that has matrix multiplications and ReLUs, and it's polynomial size, of course. OK, great. So next result is actually you can even show hardness even in an approximate sense, that it's going to be very hard to sample from a distribution that's close in total variation distance to the conditional. Okay, so this is also just coming from the way this.
So could you use the? I mean, the neural nets are p-complete. So could you just have a formal evaluation or throw it into a PCP or something?
I don't know. You need to be a little careful about at least the way that that my student is doing this gadget. Not only because the input doesn't have to be integer value. The input can be real value. So you have to make sure that for any conditional sampling, after you round the output of n of x, you will get a satisfying assignment. So that needs a little bit of technicality. But I think you may be able to strengthen the hardness here. So the next thing is, OK, it's probably hard, but let's still try to do it. So one way that we can still try to do these things is with variational inference. You would like to find a neural net that samples from the conditional distributions. So if you just try vanilla to train a sampler for the conditional distribution, it doesn't work. But there was an interesting way that, so this is an example of our experiment where it doesn't work. So you have this face, you're missing these pixels, you want to do conditional sampling, and you see after 60 hours of training, it still produces pretty bad images. So this is the key idea I want to tell you. We're going to use variational inference for a composed generative model. So somebody has already trained this great invertible generative model that produces faces. But I don't want to dream of a face. I want to dream of a face that agrees with my face up to these pixels, right? So I want to do conditional sampling. So training it end-to-end didn't work. But the key idea that I'm going to do now is, instead of feeding it some random noise that was Gaussian, I'm going to train another network, let's call it f hat, that takes some random noise and produces a good noise. What's a good noise? A good noise is a noise that produces something that agrees with my face up to here. Is this making sense? So a good noise is a noise so that f of that good noise agrees with my observations. If I had a way to sample from good noises, I would be producing conditionally good samples, right? How the hell am I going to sample from the good noise? I don't know. I'm going to train a net to do it. So we're going to, so this is the key idea. So I mean, I guess it's getting technical and I'm running out of time, but you can define some distributions. This is the composition. F is the network that produces the images. F hat is the network I'm training over. This is the probability of the composed model. The important thing I want to say is this is the probability of the composed model of x1. x1 is the other half of the image you don't get to observe. This is the marginal, and you cannot marginalize an invertible generative model. We can prove that, okay? So if you wanted, if you had a way, if you needed to just vanilla do it using inversion, using marginalization, you're not going to do it. So we cannot directly minimize elbow for a composed generative model. And the idea of my student was to basically do this smoothing. Instead of observing the conditioning, you add a little bit of noise to the conditioning, and then you can write a variational loss that you can actually optimize over. So I guess in 1 minute, I'm running out of time, but this is the thing you would like to search over. You would like to find an f hat, that's the initial model. So the Kullback-Leibler of the total end-to-end construction is close to the conditional distribution. So you massage this thing, and what you get down to is basically this form, which is extremely natural. It says, find the pre-network so that the noise that it generates looks like Gaussian IID, right? That's what this term says. Plus, if you sample from this good noise, you actually agree with the observations. So these are the two terms that this boils down to, and both of them have an extremely natural interpretation. So just some results quickly. This was the thing that wasn't working, but if you train the conditional sampler like this, you get many samplings. Here is one example. You observe upper half of a face. I want you to see that the completions this model produces, this is called real MVP. It's an invertible generative model. It has diversity. Do you see that it's not producing the same mouth all the time? It just produces many, many mouths that agree. This is the original image, which is different, of course. And you can also measure the variance. Like you can just get samples for every pixel. You can tell me how much you trust each pixel, right? And the pixels further down are less trusted, of course, because you don't know how the hair is going to move. So you can do the same thing for super resolution. You get a blurred image, and you get many deblurrings. So, and of course, the real image is different, but that's fine. And you get also how much you trust the reconstruction. And it's very nice that you have uncertainty exactly where you would think. So they found it cute to do my face. It's important here to emphasize that I am really out of distribution for a number of reasons. First of all, because of the beard and the glasses. And also, this image is actually particularly hard because it's tilting. So it actually tries to make it not tilted, you see? So, that was my, not as entertaining as making Costis female, but that's a punchline here. So, let's talk back to 1 minute. Okay, all right. So historically, we have been families of modeling high-dimensional distributions, sparsity, as I said, and conditional independence. These things gave us, compression and LDPC codes. But now we have these deep generative models, which pass simple randomness through a learnable differentiable function, and they're extremely expressive. So all training and inference tasks use gradient descent, and all of them are poorly understood. So this is an extremely fertile area, in my opinion, for people to have contribution. So if you want the short answer, it's wherever you have a paper that says X is k-sparse, replace it with X is in the range of a deep generative model. And just conclusion, we need ways to model distributions. And currently, deep generative models are the state of the art for many real data sets. And we need provable algorithms for inversion. So I spoke briefly about this. But gradient descent practically works sometimes, but we have no proof. There was a paper by Paul Hunt and Vlad Voroninski that showed that if the generative model has random weights, gradient descent provably solves this problem, which is quite remarkable. But it requires the network to have a lot of growth in its size in every layer. So that's also a little bit analogous to your question. So I think diving into this question more theoretically is very interesting and important. Fitting generative models to data is, of course, another huge problem that many people are working on. And even evaluating if a generator really fits a data distribution is a hard problem. So there's a lot of open problems here, and you can find more information on my homepage. So I will stop here. Thank you very much for your attention.